Good morning and welcome to the 29th annual exhibit of hydrogen and fuel cell technology. We've been here for quite some time talking about the advantages of the technology for net zero emissions. We need to distribute the hydrogen that is created. We need to create more green hydrogen, but we have to ask ourselves what we're going to do with it, how this distribution is going to occur. This is among the topics I'm going to be talking about with Professor Gunther Kolb, who's from Fraunhofer IMM. We'll be talking about ammonia as a sustainable hydrogen carrier. Please welcome with me Gunther Kolb.
Hello.
Hello, Professor Kolb. So, everyone in Germany knows, of course, Fraunhofer, but some people from foreign countries, they don't know of this massive facility in Germany that does science. Could you tell us a bit about Fraunhofer?
Yeah, of course, it's the largest organization for applied research in Europe. So we have about 78 institutes all over Germany, but also internationally located. And we are working in many fields very close to industrial application. And one of them is, of course, research in the field of energy. We have an energy alliance of all the institutes which are active in that area. And that covers everything from energy distribution to power grids and then also hydrogen, of course. And our institute, where I'm working at, is Institute of Microengineering and Microsystems in Mainz. And we are dealing with the generation of hydrogen out of hydrogen carriers, such as methanol or ammonia, or other hydrogen carriers, bioethanol. And we also work in the field of methanation of biogas, CO2. And we have a large test facilities for people which are interested in testing the equipment with large gas flows and humidifying large gas flows and such things.
This is, it's always fascinating how complex and yet how elegant and simple some of these equations are. We all know hydrogen is only an energy carrier in this field. It doesn't, you can't put a hole in the ground to get hydrogen out of it. You need optimally renewable resources, and you convert it to hydrogen because batteries will not do it for the terawatts. So once you have hydrogen, which is this really wonderful molecule, the question is what best to do with it. Often you can use hydrogen right away in PEM cells for electricity, but here's where it gets interesting. One of your really huge strengths is what to do with the hydrogen molecule. What are the options? What can you do with a hydrogen molecule if you don't use it immediately? And what do those conversions look like?
Yeah. So the point is that hydrogen can be generated here in Germany, but the quantities are limited. Yeah? We cannot cover our complete energy demand with the local generation. And that means that we have to move to other places, and obviously it's much more convenient and energy efficient to move to places where there's a lot of wind or a lot of sun. Could be, just as an example, could be Australia or Chile, and generate the hydrogen there from photovoltaics or wind power. Once you have generated that hydrogen, it needs to be transported to the areas where there's a huge demand for it. And that can be done in compressed or liquid form. But if you look at the features of liquefied or compressed hydrogen, you will find that it's much more convenient to use hydrogen carriers, yeah, such as methanol, or even more prominent, such as ammonia. Now, generating the hydrogen by electrolysis consumes a lot of energy. And if you compare that energy consumption to the energy demand for making ammonia out of that hydrogen, you will see that the ammonia synthesis, it's only a small percentage, maybe 5% of the total energy demand. From going from electricity to hydrogen is 95%, and 5% on top to make the ammonia. And the same applies if you look at the same applies for the cost. So the cost of the electrolysis is much higher than if you look at the cost of the ammonia synthesis. Once we have that ammonia, we have a molecule which is already on the market, a bulk chemical, one of the major bulk chemicals worldwide, and it's transported in huge quantities every year for a long time already. There's established technology for that. On the ship, on the rail, ammonia transportation happens every day in million-ton scale. And it's an important molecule, and most of you know if that molecule wouldn't exist, mankind wouldn't exist in its huge number now, because we use that for making nitrogen fertilizer, and by that we get enough food for all the people which are on the planet right now. And that is also one major step to make that ammonia synthesis green, as a first step to make the fertilizer production green.
It's all about the big word, of course, it's decarbonization, right? To decarbonize, what do we need? Decarbonize the steel industry, decarbonize the agricultural industry, and a pile of other industries. That is using industrial gases that are not created from holes in the ground, the traditional hydrocarbons, oil and natural gas. For me, we'll return to this carrier construction here. The whole discussion about hydrogen, you don't often hear the issue of, oh, transportation. You don't hear the issue that we're going to be trading massive quantities of energy in the form of hydrogen, hydrogen converted to something else, as we do with oil. This is the goal. And it's going to involve a lot of shipping. It's going to involve pipelines, new concepts of distribution. And all of this is necessary because we're decarbonizing not simply the electrical grid. That's 15% of the energy consumed in Germany. It's the 85% that is difficult. So ammonia is fascinating, isn't it? It's a start case. That is, ammonia already has a direct application. Before we talk about it as simply a carrier, you can simply say there is a demand. And there may even be a reward for using green ammonia. Or traditional sources may become less available. Could we generalize about the process, though, of conversion? There are discussions about e-fuels. And you're the specialist. You surprised me last year with this efficiency concept. What else can you do with the hydrogen molecule? And what other applications are there? Not directly addressing perhaps the question of hydrogen and how it's being carried, but what other fuels can you do effectively with the hydrogen molecule? Can we replace methane? Can we replace other industrial chemicals with hydrogen?
Yeah, of course, it's also feasible to generate synthetic natural gas methane out of hydrogen. We can synthesize methanol out of the hydrogen, preferably using CO2 from the atmosphere. So there are many options, and what people sometimes think about when they say e-fuels, these are fuels made synthetic hydrocarbons, which are very similar to what is consumed nowadays. Yeah? But in the future, I would say ammonia is an e-fuel as well. So we should be a little bit careful how to name things and get it in the right order. Yeah?
It is confusing because the debate now, and I'm sort of having two conversations at the same time, this whole debate about e-fuels is addressing the potential to extend the lives of combustion engines. I have to ask the opinion of a specialist here because does that make logical sense? We can, for industries such as the airline industry, create e-fuels. And maybe they are necessary in some applications, and that sounds wonderful. But what is the efficiency loss when we think of e-fuels, which many people do, as something you're going to tank your car up with? And nothing's going to change. You can still use your combustion engine. What are we talking about in terms of efficiencies when we don't use them, for instance, in a hydrogen car or an electric car, but drop them into a combustion engine?
The efficiency of small combustion engines is very low, yeah? The low 20s. Yeah? So if you compare that to a fuel cell, that is, of course, much more efficient already at that size. On the other hand, you have to admit the very large engines for maritime applications, for huge freight transporters, vessels, is quite high. Yeah? So it might be an option in that area to still use combustion engines because they reach very high efficiencies. Yeah? So we have to look at the application and not stick to one technology. And another issue is that in case we have a transportation, as we said, from Australia all around the globe to Europe, that will be the only option, most likely, to ship it here as ammonia. And when the ammonia will be here, you can have a centralized decomposition and then distribute the hydrogen as a gas, even though we know that the hydrogen is not so easy to be transported. So why not distributing the ammonia? Why not thinking about also distributed utilization of ammonia, making hydrogen not only in the industrial sites, but also for the demand as an energy carrier. And that is where our technology comes into the field. So this is a decentralized decomposition of ammonia, and we think there's a huge potential for that also in future. So that can be, for example, to feed hydrogen filling stations, perhaps not for passenger cars, perhaps more for trucks, for heavy freight transport on land. That could be as well feeding combustion engines fueled by ammonia. Yeah? So you cannot burn the ammonia directly in the combustion engines, but you have to crack it at least partially. So you have to have some 10 to 20% of hydrogen in the feed of the engine, and then the combustion works. And such cracking reactors is also one field we are dealing with. Yeah? We have a unique reactor technology developed over the last 2 decades, which allows the very efficient utilization of catalysts and heat flows in such processes. Such processes also as ammonia decomposition, which is a reaction which consumes energy, and we can use off-gases of this process to make the efficiency of the overall decomposition process higher than what is possible with conventional technology. So conventional technology maybe has an efficiency of 70%. With our technology, you can reach 90%. And if you look at decentralized or even mobile application, compactness is also an issue. And with our technology, with small microchannels, we can get very good utilization of the available space and get a size reduction of 90% compared to conventional technology. And that is important for mobility, to have compact solutions.
Yeah, I always, when I hear the keyword efficiencies, I have to smile because there's a positive and negative way of looking at that. We have had people discussing the lack of efficiency of solar panels. Only 50% of the sun's energy is captured by the solar panels. The joke is, what do we need to know? If the kilowatt hour is cheaper than what we're paying for other forms of electrical out, that's what's interesting. This is the interesting side of this equation. We start actually with affordable forms of renewable energy. They are extremely affordable and the prices are dropping. How much does this question of efficiency play in to how we calculate these things? I get the idea, the more efficient, the more energy, right? There is also another way of looking at that. Once you convert to a certain energy carrier, hydrogen is an energy carrier, but it's lousy to transport, you convert it to something else, you have to have applications that work efficiently with what you produce. You could produce methane and find an application for that. How do you actually look at the question of efficiencies? People really want to know what the kilowatt hour costs, or if you're in industries that use hydrogen, you want to know the price per kilogram. Is there any way of looking at that from a financial or business model and saying, what can we offer?
So, I mean, the price of the ammonia generation, of course, largely depends on the price of the solar energy, for example, available. Yeah? And that is much, much lower, of course, in countries where there is a lot of sun. So that determines the overall price largely. As I said, the electrolysis is by far the most cost intensive step of the whole chain. Even the synthesis of the ammonia, the decomposition don't count up much on that. Yeah? So it's mostly the electrolysis, and that is also, once there's a large enough capacity of electrolyzers built and installed, yeah, by an economy of scale, the price will go down, and we will have very, very cheap electricity in such areas. Yeah? And that will make it affordable for sure.
Let's return to the question.
By the way, sorry, I just forgot. We even have to consider that there was a huge ammonia production already. Maybe I mentioned that before, but there was a huge ammonia production in northern Europe already, and by electrolysis, yeah, as we want to do it now, and that was stopped because the natural gas price was so low. And it's really, actually, it's a shame. We have to go back to the past and look what happened there. Yeah? So it was feasible. It was economically viable at that time. Yeah.
Yeah. Don't get me started on the mistakes made in that. We gave up our energy security by stopping the use of coal. Even though natural gas vents more methane, but it's not vented in Germany, so you don't need to count that into the eco-bounce, how decimating that is to the atmosphere. It really is a complicated issue, but what we're addressing here, and this is the topic of the whole talk, sustainable hydrogen carriers. I don't know whether there's any effective way to accentuate what exactly we're talking about. We're talking about approaching a world distribution of renewable energy. The scale is unimaginable. When you talk to the guys who do electrolysis, we're going to have football stadium-sized electrolysis facilities as we do gas and oil refineries. These are going to be massive investments with high returns, and you can see the change in the industry. The amount of space occupied by electrolysis companies here has just exploded over the last, I think, 7 years particularly. How large are these challenges, and how much we may be underestimating how easy it is to do what you do, which is simply take the math and know that there's technologies to convert the hydrogen molecule to other things, and it's effective. I think maybe we're underestimating that that's the easiest part of the whole solution. What is your take on how difficult it's going to be to get to the point where we have a net zero hydrogen economy, which involves distributing hydrogen stored in various combinations as a commodity?
So I think that there will be also, of course, local distribution of hydrogen in shorter distance. That is feasible, but it has to be considered that there is really a need for different solutions for different scenarios. So that is important to understand, I would say.
Okay, there's so much detail, and of course, we cannot underestimate. For years, I've had the privilege of talking to you on the stage here. This is the man who's continuously shocked me with the efficiencies of converting hydrogen to other forms of gases. I was always skeptical because I assumed there'd be a big loss of energy there, and in fact, it's simply not true. To get more details, though, you should go to the Fraunhofer IMM booth, which is B42, and talk to Professor Kolb there. He's the expert on the fair on the issue of what you can do with the hydrogen molecule, the specialists in catalysts. For decades you've been here, and it's been a pleasure to talk to you. Thank you very much, Dr. Kolb.
We also have a Fraunhofer booth in Hall 16, and there you can take a look at our ammonia decomposition system as well. So